So how can we define crack? A crack is a localized breakdown of bonds in material. It could be internal or a scratch on the surface, as you can see in the figure here. So a crack will form in material either inside or on the surface, and then the crack will grow and it will get longer. Remember that cracks in materials under load a stress concentrator. A stress concentrator is any discontinuity that will amplify and applied stress. The stress cannot be transferred through the crack, and therefore stress is concentrated at either side of the crack. And the transition from that slow, stable to the fast and unstable phase is right when the crack becomes critical and finally reaches a critical length. So how do we quantify a crack? So let's say that we have materials and we apply stress to it. Let's call it a sigma naught. Let's say inside the materials we already have a crack here. We are going to generalize that the shape of the crack as an elliptical crack, like I show in this figure. And at the tip of the crack, we can see a small circle here that shows the sharpness of the crack, and the radius of a curvature, we call it rho. If the radius is small, then we call it a sharp crack, but if the radius is large, then we call it as a blunt crack. And we can also quantify the length of the crack as a 2a. So from all these values, we can quantify the stress concentration factor. We have the K sub T here. We have a K sub T is equal to the maximum stress at the tip of the crack divided by the applied stress. And this is roughly equals to the 2 times root A or half length of the crack divided by rho, or the radius of a curvature. So the process of a fatigue failure is characterized by a crack initiation where a small crack forms at some point of a high stress concentration. Then we have a crack propagation where the crack advances incrementally with each stress cycle, and a final failure where it occurs very rapidly once the advancing crack reach a critical size. And here a typical plot showing the growth of a crack is provided here. Notice that the crack initially grows very slowly at this phase. And the reason, but the growth we can see the growth accelerates as the crack size increase. And the reason for this acceleration in growth is that the growth rate is dependent on the stress intensity at the crack tip. And the stress intensity factor is dependent on the crack size, A. As the crack grows, the stress intensity factor increase, leading to a faster growth. And the crack grows until it reaches a critical size, and finally failure will occur. So now we will talk about the Griffith crack model. As we already know, flows are stress concentrators, and stress will be concentrated at the crack tip. And if it is assumed that a crack is similar to an elliptical hole to a plate, like what we can see here, and is oriented perpendicular to the applied stress, the maximum stress sigma m occurs at the crack tip and can be approximated by this equation. So here we have sigma m. Sigma m is a stress at the crack tip equals to 2 times sigma naught. Sigma naught is applied stress times the square root of A divided by rho sub t. A is the half size of our crack here, and rho sub t is the radius of a curvature of a crack tip. And sometimes the ratio of sigma m divided by sigma naught can be denoted as a stress concentration factor, that is a K sub T. And the effect of a stress tracer is more significant in brittle than a ductile material. So for a ductile material, plastic deformation happens when the maximum stress exceeds the yield strength. This leads to a more uniform distribution of stress in the vicinity of a stress tracer and to the development of a maximum stress concentration factor less than the theoretical value. And all brittle materials contains a population of small cracks and flow that have a variety of size, geometries, and orientation. So when the magnitude of tensile stress at the tip of one of these flow exceed the value of critical stress, then a crack will form and propagate. And what happens is it will cause a fracture of the material. So we know that fracture stress depends on the crack size. We also know that fracture stress depends upon the material properties such as stiffness. And the first person to establish the quantitative relationship between fracture stress and crack size crack size and stiffness was Griffith. And Griffith attributed the discrepancy ataupun percanggahan. So Griffith attributed the discrepancy between the observed fracture strength of a crystal and the theoretical cohesive strength to the presence of flows in a brittle material. And this theory is applicable only to a perfectly brittle material such as glass and cannot be used directly to metals. So let's say consider a white sheet of unit thickness of a brittle material, as you can see here, and it has a lens shape, a crack of 2C or 2A length, which runs from the front to the back face here. So when we apply longitudinal tensile stress, the crack tends to increase its length in the transverse direction. Or we can say in a perpendicular direction to the tensile stress. So when the crack spreads, the surface area of the crack increase, but the elastic strength energy stored in the thin sheet decrease because of elastic strength and continuous across the crack region. So the critical stress required for crack propagation in brittle material can be described as sigma C equals to 2 times E times gamma S divided by pi times A to the power of half. E equals to a modulus of elasticity, gamma S equals to specific surface energy, and A is the 1/2 of the length of an internal crack. So in short, we can say that any crack or imperfection limits the ability of a ceramic to withstand a tensile stress, and this is because the crack, or sometimes called a Griffith flow, will concentrate and magnify the applied stress. So when a crack propagates, the elastic energy release in the volume of material, and the two new surfaces created, and crack propagates if elastic strain energy release higher than the surface energy. The crack or imperfection will limit the ability of a ceramic to withstand a tensile stress, and this is because the crack concentrates the applied stress. So the measured fracture strength for most materials are significantly lower than those predicted by theoretical calculation based on atomic bonding energies. And this difference is explained by the presence of a microscopic flow or crack that always exists under normal condition at the surface. and within the interior of a body of a material. And these flows can cause damage to the fracture strength because an applied stress may be amplified or concentrated at the tip. The magnitude of this amplification depending on crack orientation on geometry. So this phenomenon is demonstrated here in the figure. You can see a stress profile across a cross section that contains an internal crack. So as indicated by this profile, as we move away from the tip of the crack, we can see that the magnitude of this localized stress will reduce with the distance away from the crack tip.
And here we have a question that says that a relatively large plate of glass is subjected to a tensile stress of 40 megapascal. So if the specific surface energy and the modulus of elasticity for this material is equals to 0.3 joule per meter squared and 69 gigapascal respectively, can you determine the maximum length of flow that is possible without fracture? So here in this question, what we want to determine is the maximum length of flow that is possible in material without a fracture occurring. And this is the equation that we will employ to solve this equation. So in theory, the theory of a brittle fracture mentioned that based on this equation, we have a sigma c equals to 2 times E times okay, the theory of a brittle fracture mentioned that based on this equation, we have delta C equals to 2 times E times gamma S divided by pi A to the power of half. So where A is equals to the length of surface flow, and gamma S is the specific surface energy, and E is the modulus of elasticity. So what we want to determine in our question is we want to determine the maximum length of flow that is possible in the material without a fracture occurring. So on when we rearrange this equation, what we get is A, or the length of the surface flow, equals to 2 times E times gamma S divided by pi sigma C to the power of 2. So A equals to 2 times 69 to the power of 9. This is the modulus of elasticity times 0.3, the specific surface energy, divided by pi times 40 to the power of 6 to the power of 2. And hence, the maximum length of surface flow, A, will be equals to 8.24 micrometer, or 8.24 times 10 to the power of -6 meter. So this is how we determine the value of A, or the maximum length of flow that is possible in the material without fracture occurring. Thank you.